Welcome, everyone. Today is Dana's 90th birthday, so happy birthday, Dana. And thank you all for being here. We're so glad people have joined us here, but also many, many people on Zoom and on YouTube to celebrate Dana's life and work. I hope you don't mind if I briefly introduce where we are. So we're streaming from Berkeley at the Topos Institute, and we're a new international research institute nonprofit with a mission to shape technology for public benefit by advancing sciences of connection and integration. In this time when there are many global challenges facing us, from climate change to rising mistrust in democracy, and it's at a time when technology is a significant driver of these changes and has the possibility to be both hugely positive and hugely negative. Our vision is to help build a world where the systems that surround us truly benefit all. So this problem is multifaceted, but a great tool we have to shape systems in the world is logic and programming languages. And we're immensely privileged to count Dana as one of our earliest supporters and as a senior advisor. Few people's work inspires like Dana's does. We'll say many words today, but to me, Dana's drive to precisely name what we mean in our formal languages, to figure out what we can say, and by extension, what we cannot, leaves a scientific legacy of immense importance. One we are so grateful for, and one we celebrate today with the seminar by Gordon Plotkin. So again, happy birthday, Dana, and thank you. Before we move to the seminar by Gordon, we're fortunate enough to have Dana say a few words. So to Dana. Sorry.
Yeah.
Great. Thanks, Dana.
Thanks, Brendan. Good morning to all of you I can see and those I can't see. You know, I never expected to live to my 90th, and I would never have imagined I would be seeing a world faced with destructive wars, natural disasters, pandemics, and bitter political fights. But I don't want to be gloomy today, so let me briefly summarize some personal history with a few key dates. Going back a long way, my father was born in Fort Bragg, and my mother in Susanville, that's very far north California. They met in Fort Bragg and were married there in 1922, 100 years ago. I was born here in Berkeley by mistake. That's another story I won't go into just now. I was born here by mistake in 1932. My future wife, who's here with us today also, Irena, emigrated from Austria with her widowed mother in 1939. And so the two of us have so many California roots. Now, I lived in many Northern California towns before graduating from high school in Sacramento in 1950. And I was luckily able to go to UC Berkeley, where I graduated in 1954. With more good luck, I was accepted at Princeton and got my PhD there in 58. My first job was an instructorship at the University of Chicago, and there I married dear Irena on the 10th of October, 59. So yesterday was our wedding anniversary. We moved here to Berkeley in 1960 when I was appointed assistant professor at Berkeley here in the math department. But then in 1963, I moved to Stanford, and our daughter, Monica, was born there in 65. After a sabbatical year in Amsterdam, I met Christopher Strachey in the summer of 1969 and decided to work with him at Oxford during the fall term, before taking up a new position at Princeton, which I then did in 1970. But then out of the blue, while I was at Princeton, I was elected to the first professorship of mathematical logic at Oxford. And I went there in 72 and remained until 81. Now, while I was at Oxford, I became aware of a very noisy graduate student up in Edinburgh, one Gordon Plotkin, very noisy. I knew many colleagues up there, including his thesis advisor, and over the years, his work and my work have intersected, I hope, in very many productive ways. It's a great pleasure that he could be here to speak today. At Oxford, I also was especially lucky to have a moderately noisy graduate student of my own, Michael Foreman, and we had a steady collaboration and work with many colleagues in the UK and other European countries, in particular to promote an informal and unfunded peripatetic seminar in sheaves and logic. The first meeting took place in May of 1976. This movable seminar has now had more than 105 meetings. I think they had to pause on account of the pandemic. I hope it will pick up again with various people. Although the name has stuck to it, the talks are not very often about sheaves and logic anymore, but more on many aspects of topos theory and category theory. Mike has been an Edinburgh colleague of Gordon's for several years, though they're both now emeritus. And of course, it's especially nice that he could be with us here today to remember old times in particular. I moved to Carnegie Mellon in 81 and was on the faculty for 22 years. Our daughter finished high school in Pittsburgh and then got her college degree in music at Oberlin. After a period in Europe, she returned with her husband-to-be, and we were able to celebrate their marriage all together in Pittsburgh. In the early 2000s, they moved to Berkeley, and our two grandchildren were born here in Berkeley in the hospital of the same name that I was born in. It's not the same building, but there's that connection. And then Irena and I moved to Berkeley in 2004, and as grandparents, we're so lucky to have seen our grandchildren grow up. So many grandparents complain that they don't see their grandchildren enough. So we are very, very, very lucky. Another reason that we're very lucky is that, another reason that I am very lucky is that classical music has always been a very important part of my life since early times. So it's especially meaningful to me that my wife, my daughter, and now our granddaughter, Magali, are all music professionals. And they're a terrific trio together. Too bad they can't perform today, but maybe a YouTube can be put up so you can see how amazing they are. The University of California has lots of assets, and coming back here, I was very glad indeed to be welcomed by old friends and new colleagues in EECS and mathematics, especially in the logic group, of course, in philosophy. But I want to point out there's also MSRI up on the hill, and I've known personally all the founding and past directors of that institute and have benefited from so many of their programs and other events over the years. It must be the most successful mathematical research institute created by the National Science Foundation. This year, they're celebrating their 40th anniversary and have just become the Simons Laufer Mathematical Science Institute because they have an amazing new endowment. It's just such an asset to Berkeley here. Berkeley also has the Simons Institute for the Theory of Computing. It's now celebrating its 10th anniversary. The founding director was Dick Karp, a very old friend, And everyone here was especially happy to welcome Shafi Goldwasser when she became the new director in 2018. I've benefited from several of their many programs and visitors from around the world. These two institutes will continue to enrich research here at university for a long time. But wait, there's more. There's the Topos Institute, where we are today. As we heard from Brendan, who's the chief executive, and David Spivak, whom I've known for many years, is the chief scientist, treasurer, and secretary. It focuses on many applications of category theory, topos theory, and type theory. I've known many people associated with the Institute, but I became very engaged with their summer intern program. So during this last June, July, and August, I tried to answer 1,000 questions about domain theory and denotational semantics. It was a quite intense time for me, but I had a very sobering experience. While trying to remember details of things I had forgotten, I had to deal with Google Scholar. Just a few names or keywords resulted in a list containing at least a dozen or more papers I should have recalled, should have known about it, or worse, I should have read. One sees in Wikipedia that not everybody is happy with Google Scholar, but time after time, I found it absolutely essential. And I don't even go to the library anymore because there it is available online. My two interns and I collected a Dropbox folder this summer of over 200 items that might help for future research in the topics we considered, and I hope it can be somehow organized so it can still remain useful. So on many, many fronts, I give my very special thanks to Topos, the Topos Institute here, for all this stimulus, support, and especially for hosting this seminar and celebration today. Thank you so much. Enough from me now. It's time to hear from Gordon Plotkin on the topic, does recursion help? I hope it helps. Oh, I still have the info. Here it is. There we go. There you go. Yeah.
Oh, thanks.
Okay, is the mic working okay? Yeah. The mic working okay? Yeah. Okay, great. Well, I don't know what noisy means. So maybe it's a technical term of some sort. I think it's positive, but it'll be useful for a seminar. Well, here I am. It's a huge honor, an amazing honor to be speaking here on Dana's 90th birthday symposium. It's a pleasure, or it will have been a pleasure, not quite yet a pleasure. We go back so many years, it's something like 50 years. We were talking and discussing. Dana would send me comments and they would all be colored. There was a kind of coding scheme, blue, red, and yellow, but I don't remember what they were, but it's very pretty too. It's very pretty. So I don't have any pictures of us together, but here's a few pictures from 50 years ago, plus or minus. There would be three pictures. Help. Yeah. Why, oh, why?
You might need to click on the actual app and
Computers are great when they work.
Yeah. Oh, cool. Okay, so a picture I really like. This. Where's it gone to? There it goes. The Dana and Monica from a young Monica. I think it's such a beautiful picture. I think this could be a paint with some kind of Renaissance painter on the wall. It's just lovely. I'd like to just stay with that for the rest of the seminar. But here's a picture of Dana lecturing June 1968 with technology 0. I noticed to give seminars in those days on lambda calculus, you needed running water. That's clearly important. So I tried to get a picture of me, and I kind of succeeded. So anyone know who the other two are? Yeah, who's this then? That's a harder one. A colleague of Frank, yeah, Jan Willem Klopp. Yes, in his early, very bearded sort of stage. Anyway, so there we all are from all that time ago. So this is a kind of a present. This seminar is a kind of a present. So a present should be something that the receiver enjoys receiving, and I guess in this case hearing about. So this is about the lambda calculus, an old interest of Dana's. I don't know, 1960s, you were already writing about lambda calculus. There are Scott numerals, but I'll be talking about Church numerals today. And interestingly, to prove a theorem about these Church numerals, I'm going to use domain theory. So I hope you'll like the present. You better like the present, or I'll be disappointed. So this is what everyone knows, or largely knows. In the untyped lambda calculus, you can do everything in a word. So we've got a standard coding function which sends natural numbers to the nth Church numeral. So that's, and you represent numerical functions. You say a closed term lambda beta represents a partial function f. If whenever f is defined it sends m to n, then the lambda beta says it does with the representing term f. And in case it's undefined, then f there has no beta normal form. So that's kind of as good as you can get syntactically for being undefined. And then a theorem, I mean, jointly from these people, is that three things coincide. The lambda beta representable functions, well, I should say in parentheses, that's the same as the lambda beta eta representable functions. So it doesn't matter. And the Gödel-Herbrand partial recursive functions and the functions computable by a Turing machine. It's interesting to see the two different characters of these two representations. In this one, you represent the class of functions by schemas. This is the least class of functions closed under ... minimization, partial recursion. And here, it's a different kind of characterization. It's by an automaton. Okay, and so we'll see dim reflections of that in the typed case. So what happens anyway if you go to the typed case? So here's a typed case. We represent, now everything has to be typed, so we have to have a type of natural numbers. So standard one is omicron, arrow, omicron, arrow, omicron. People say, which is functions to functions, and people look at that and say, why, what? But if you think about it, what an element of this type says, if I have a 0 and I have a successor, I'll build you a natural number. So it's quite sensible when you look at it that way. It might have been more transparent if you written it as omicron, arrow, omicron, arrow, omicron, arrow, omicron. Then it said, I've got a 0 and a successor, instead of saying I've got a successor and then a 0. Okay, then the coding function sends n to the nth Church numeral, the typed one, the f to the n. And defining functions, now we're in the typed lambda calculus, everything's going to be total, everything terminates. So,
Excuse me, what's
sure.
omicron here?
Oh, sorry, that I forgot to say. So this is the typed lambda calculus for single base type omicron, thanks. Yeah.
So it's individuals of some kind.
Yeah, individuals, individuals. So a term represents that if fm equals n implies that lambda beta says so. And it's a little mental exercise to say that this implies, but this implies the reverse implication. If you want to think about something for a second.
You went from partial functions to total functions here?
I have to be in total functions because I'm in the type lambda calculus.
All right.
Yeah, so I don't have any choice. I will have a choice, but not with this lambda calculus. And that'll come up pretty soon. So the theorem due to Schwichtenberg and Statman is the representable functions are exactly the extended polynomials. And just tell you what the extended polynomials are. And notice this is given by a scheme, okay? So there you have these constant functions, 0, 1, projections, addition, multiplication, and this tests for 0 functions. So if L is 0, you give M, otherwise you give N, okay? So actually, if you think about it a bit, and I hope this is correct. This is the same as saying, here's a function of some arguments. You do some tests which arguments are 0 and which aren't. And then for the result of each test, you just emit some polynomial. So you might say if x is 0, then x squared plus y squared. If x isn't 0, then x cubed minus 5. You know, so that's equivalent to it. Yeah, so that's right. So the question is, does recursion help? Because in that very first theorem, when you're looking at the partial recursive functions with the untyped lambda-calculus, lots of recursions go on. So why don't we just add recursion to the type lambda-calculus, and surely we'll get all partial recursive functions. But the question is actually can be extended more than that. That question would be fine, but it'd be limited. It'll only be talking about the Church numerals, what you can do with the Church numerals. So I want to say a little bit about what one can define in the type lambda-calculus to show there's a wider question than just that. So first of all, instead of a omicron arrow, omicron arrow, omicron arrow, omicron, for any sigma, you can do the same thing, sigma arrow, sigma arrow, sigma arrow, sigma. And you could just as easily, the same programs which gave you the extended polynomials, if you just change omicron to sigma, they also give the extended polynomials here. But you can get more. So, but you can get more in two different ways. One is a non-uniform way. So here's a function of k arguments. And we're using different sigmas for all the different arguments and results, so possibly different. It seems reasonable to call that non-uniform, though other authors call it non-strict. Anyway, it doesn't matter. I'm calling it non-uniform, or have this uniform representation. They should all be the same. So the question, well, first of all, can we define anything new? And does it make any difference whether we're uniform or non-uniform? For a long time, people thought it didn't make any difference, but no one had a proof. But in fact, it does make a difference. So these folk, Fortune, Levin, and O'Donnell, show that predecessor is non-uniformly representable. And I'm going to randomly attempt Polish pronunciation. Zakrzewski showed that predecessor is not uniformly representable. So they're actually different. So that's really quite interesting. Okay, here's Zakrzewski's conjecture. The class of uniformly representable numerical functions, the smallest class, and again, schematic type characterization, you have to add two schemas. This is the easier one to understand. It's another predicate, less than m. If m is less than L, then you give 0, otherwise you give 1. This one basically says we can do arithmetic modulo. So the arguments, you look at m modulo L, this is for any L, you find the modulus, and you suppose the modulus is 3. Then you take the third of these arguments. Okay, so you select. Okay, so he obviously showed that all of these things are uniformly representable, but not all with the same alpha. You're allowed to change your alpha. The question is the converse, and that's open as far as I know. Okay, so that's one thing, but we can work on things other than numbers. For example, trees. So think about binary trees whose leaves are labeled a 0 and a 1. So following the same principle, we need a function which have two arguments, a 0 and a 1. So that's this omicron, this omicron. We need a thing that takes two trees and makes another tree. Okay, and then we get a tree. And you just follow out that recipe in this circumstance. So 0 is lambda x, y, f, x. 1 is lambda x, y, f, y. And here, cons, you take two trees, T and U. You feed T and U the recipes for making a tree. So we get two trees. I mean, two tree recipes. So you take two tree manufacturing objects. You feed them the recipes for making a tree, and then you combine them with F. Okay, so that's what you might expect. And then we can define gamma just by induction after that. Okay. And so Mark Zion's proved Schwichtenberg Statman type results for algebraic data types. So you can carry on doing that kind of thing. Here's another example. So this is a connection with automata theory. So let's do strings. So first of all, Booleans, you just have a true and a false. For binary strings, you need the empty string, you need the adding a 0, and you need adding a 1. Okay. And you just follow the same recipes on the previous slide and you can get strings. The question is, what are the uniformly definable predicates? uniformly representable predicates, W alpha arrow B to B. You're allowed to use whichever alpha you like. And this beautiful theorem of Hilbrand and Kanellakis, representable predicates that correspond exactly to the regular languages. So there's connections with automata theory too. And I guess that's another connection to Dana's Turing. Well, he worked on those automata and got the Turing Award for that. That was really a long time ago too. When was that?
A long time ago.
Oh.
And I was still a graduate student with Michael Raymond,
Yeah.
1957.
Yeah.
Can I ask a quick question?
Yeah, sure. So, sorry, I forgot you've got a gold badge. You can ask any question.
Yeah, I might forget if I don't have to. Could your remarks have been carried out in any Cartesian closed category? Doesn't look like you're using anything other than closedness of the category here.
I think everything would be fine. The only thing that you might want is that your coding functions are injective.
Yeah, because you can have two low categories.
Yeah.
But the things, formulas we're showing are meaningful in any.
Absolutely. Well, so that's cute. So you could ask in any Cartesian closed category what the regular languages are. Well, that's interesting.
Okay, someone should take that up.
Make a note. No, that really is interesting. I want to start thinking about it, but I better not. Okay. So that's fine. So what I want to do is get even more general. Let's just, rather than thinking about functions in this, or let's just think about any kind of functions at all on any sets, whatever, and see what it means for lambda calculus, type lambda calculus, or not even type lambda calculus, any lambda calculus to represent a function. So suppose we fix an extension of the type lambda beta calculus. I'm not going to try and define what extension means, it's just some intuitive idea. And we need, just as we're saying with Dana, you need some kind of injectivity criteria in your coding function. So say that a coding is lambda plus injective if whenever lambda plus thinks two things are the same, they really are. When you code up x and y, and if you think the two codes are the same, then x equals y. So one point which you need to keep in mind for all the talk is that the codes are this lambda omega sigma. First of all, these are the closed terms, and these are the closed terms of the type lambda calculus, not of the extension. I'm going to keep the place where the codes are fixed. So that way I can compare different lambda calculus. If they're using different kinds of codes, well, I don't know. You could think about it, but anyway, I'm not. So for anyway non-empty sets x1k through k, xk, and x, we choose some representing types and some injective coding functions. So for example, the output of a function, an element of x is coded up by lambda x bar. So for example, if that's natural numbers, this could be some Church numeral type. It's just an example, but it could be anything. It could be the reals, it could be anything, whatever. Then we say a lambda term of this type codes now a possibly partial function if and only if if f sends these x's to xk, if and only if lambda sends it to gamma. So if it's defined, then lambda thinks it's defined and it does the right thing with the codes. And if it does the right thing with the codes, then it's defined. Yeah. That's if and only if, yeah.
Before that, there's x instead of x.
Oh, that should be x. Yeah, thanks. Yeah, thank you. Yeah. Okay. So this actually, I realized when I was preparing the talk that one can argue with this definition. You might have a stronger definition that if this is undefined, then something. And I think I should have thought about that, and that might be a better thing to do. But even then, it's not enough, because you want your class of coding functions to be closed under composition, and that wouldn't be enough. So there's some discussion to be had about a good choice of definition here, but let's take this as a working definition. Now, I can't do any better anyhow at the moment. Okay, so what extensions of the lambda calculus we're going to look at? We need an extension which allows us to include partiality. So let's just take lambda omega. we're going to extend it with a single constant of ground type. And that's going to, in our minds, stand for undefined. Obviously, we're also going to add lambda y because we want to add recursion. And so that's y is just this famous type, sigma arrow sigma arrow sigma. And it turns out, and it's an obvious conversion, it tells you it's a fixed point. And if you want Church-Rosser, this is a good rule, this particular one. It's easy to change that rule and get things that aren't Church-Rosser, but this one's Church-Rosser. Now, mysteriously, there's an additional lambda calculus here, in which I not only have an omega at type omicron, but I also have an omicron at every sigma. And you might say to yourself, why bother? You've already got an omega at every sigma. If I want an omicron at arrow, omicron, omicrons and omegas, it sounds like one of these tongue twisters. Anyway, if you got an omega at type omicron, arrow, omicron, why not have lambda x omicron at omicron, omega at omicron? Substitute randomly and sense will occur. Okay. The point is basically that omegas are magic. So the following is the case that suppose I've got some equation in some random lambda calculus and it's got some omegas in it, let's say of type sigma, then I'll get another true equation if I substitute some fixed term for all these omegas. And it's even better, it doesn't matter if variables get captured. You can still legitimately do these substitutions. Now, what's great about this guy is it gives me more possibilities of substitution. For example, I've had some term of type sigma arrow sigma, as I'm going to have. So I've got omega of type sigma arrow sigma. I can substitute a term of type sigma arrow sigma, any term. But I can't do that with this guy because m isn't of type omicron. In the end, I'd have to substitute m of type sigma for omicron. I can't do that. So for my proofs, this is much more flexible. And in fact, this turns out to be a good intermediary between here and here. So it's for technical reasons. Anyhow, answering the question of the talk, recursion does not help. It doesn't do anything for you, whatever. So we say that lambda double plus extends lambda plus is conservative. Suppose it extends it. It's conservative if it doesn't make any difference to the class of functions you can define no matter what coding scheme you use at all. And the answer is lambda y is conservative over lambda beta eta for total functions. You can't do anything else. And it's conservative over lambda omega for partial functions. So this is like a surprise. So it's a surprise present. So what should I say? Yeah, so what I want to show, I mean, how to show this. Intuitively, the intuition for this is the following. You have recursion, but you damned well can't use it. You can use it up to bounded depth, the bound depending on the type. And if you can only use it up to bounded depth, you don't have anything at all. So that's going to, so the theorem, the math is going to prove that. Okay, and that's what's going to need domain theory. Okay, here's a little consequence of it. So Zakrzewski, we saw before, he said that predecessor isn't uniformly representable. Statman proved that equality and inequality aren't uniformly representable either. Suppose we're in lambda y, then all of these are interdefinable by little programs. It's good fun to think what the programs are, but you can do that offline. But once you've got them, you can do primitive recursion, you can do minimization, and you can do everything. So if these were uniformly representable, then in lambda y, we could define all partial recursive functions. But you can't, because then we could do them in lambda beta eta. So they aren't uniformly representable.
Say again what uniformly means very quickly.
Uniformly means, so we've got these Church numerals at type sigma. They're of type sigma arrow sigma arrow sigma arrow sigma. So uniformly representable means, say a function of one argument is representable uniformly if for some sigma it can be represented by a term of type Church numerals at sigma arrow Church numerals at sigma. So we're allowed to change the type of our Church numerals when we're doing representation, but when we're representing a single function, we're only allowed to choose one kind of church numerals. We're not allowed to vary it halfway through. And that's what Fortune and O'Donnell do. They say the predecessor is representable by something of church numerals sigma out of church numerals tau for different sigma and tau. I think if I remember vaguely, sigma is really complicated and tau is simple, but I've forgotten the details. Okay, so this is a bit like old King Cole. We have to go up and we have to go down the hill of representation. So we're going up, turns out to be easy-ish, pretty easy. So suppose we have to go up from lambda plus to lambda plus plus. And suppose this is conservative over lambda plus in the sense that if I take any lambda plus terms, m and n, then I can lambda plus prove them equal if and only if I can plus plus prove them equal.
The plus here is just any extension.
Any extension, yeah, yeah. And these three inequalities are such extensions. They're extensions just by adding constants, and it's pretty easy using Church-Rosser, which holds easily for all of these things, and slightly more fuss for lambda y. So it's easy to show that if we're conservative, then it's every lambda plus representable is lambda plus plus representable. I mean, that's half of conservativity. The difficult half is going to be the opposite direction. And the proof is like nothing, because suppose f is defining lambda plus term, then that just basically means at some point in the definition, you've got a proof that lambda plus says that f does a certain job. But if f does that job in lambda plus, it'll do the same job in lambda plus plus because of conservativity. So that's easy. Going from lambda plus plus to omega plus plus to lambda y is a bit more complicated, but the idea is that if you want to simulate, you have to simulate a omega sigma by some term with a y. So the obvious one is y of lambda xx. And then it turns out there's a little, if you look at the only reduction sequence that you have, then it basically does nothing. It goes in a little loop. So it pretty well behaves like omega, so it works out okay with a bit of syntactic fiddling, which I won't go into. The cool thing is, how do we go in the opposite direction? And this is where domain theory comes into its very simple domain theory. What we need to do intuitively is I need to prove that we can only do recursion up to some bounded depth. And where can I look at bounded depth? By looking at a finite model. So I'm somehow going to have a classy finite model and show that some fact about that finite model implies some syntactic fact. And I'll use that syntactic fact to get a recursion up to bounded depth. That's the kind of a game plan. So the smallest interesting finite model is you start off with Sierpinski space. It's just got 2 points, bottom and top, bottom's less than top, and you just go up the type hierarchy in the usual way. It doesn't matter if you do monotone functions or continuous functions, everything's finite. It's all the same. We get our standard semantics, the Sierpinskis of a term m with some environment rho, which we don't need the rho when m's closed, of course. It's just standard Scott way. And we could take O of omicron to be bottom, the relevant bottom, and O of y to be the relevant fixed point, least fixed point, a la Dana. Okay, that's unarguable. But this type here is finite. So this increasing sequence stops at a certain point. Oh, it stabilizes more precisely at the point which is the height of sigma. You can't go up higher than the height of sigma, nowhere to go after that. So this thing is also just f to this power h of sigma of bottom. So that tells us it would be really cool to take a lambda y term m and look at the corresponding y term, a non-lambda y term, a lambda omega plus plus term, m twiddles, in which we take every term y and replace it by something. We have to be a little bit, there's a few somethings you might choose, but this is a good something. So this is, you take lambda f and you iterate f as many times, and you might think you put an omega in here, but actually you don't want to. What you actually want to do is put in omega sigma or sigma applied to f. The reason is we're going to need to go up and down. And to go up from here, if I only substitute y for there, this whole thing is y, or provably equal to y. And if I just put an omega sigma, I couldn't have anything to substitute because y is the wrong type for that. So that's what you choose. So that's what this second property of M twiddle is, that M is provably equal to, if you take the approximation and you substitute y sigma for the omega sigma or sigma, you get back to where you started. That's a handy thing. So that's a syntactic property, an easy one. And the other semantic property is, well, of course, we've chosen this appropriately. So M and M twiddles have the same Sierpinski meanings. So these are good properties. And so M twiddle is going to represent any function that M does. So that's going to get us down from lambda y to lambda omega plus plus. And then it won't be so hard to get down to the ground. Okay. So now it gets technical. How's our timing doing? Where? Yeah, look, I've got time yet. Yeah. Half an hour. Okay, so I won't take anything like half an hour. Okay, so we're going to look at normal forms because these are corresponding to termination, roughly speaking. And the type lambda-calculus, we have long beta eta normal forms. So they're things like that. You do a bunch of lambdas until this whole thing is of type omicron. You keep going with the eta, and then you apply one of these x's to some other terms in the long beta eta normal form, or it's a variable. I should have put that in. If you've got omega as well, then you get a wider class, which you're allowed omegas in there. Otherwise, it's the same. So this is of type sigma 1 arrow sigma k arrow omicron, this type. And it's convenient, and just to write that as sigma 1 comma up to sigma k. That's just a common abbreviation. It means you don't have to write a whole lot of arrows, but you have to remember what it means. That's the negative part of it. Okay. Now, what's amazing is, so these things are going to have different kinds of meanings. And in the Sierpinski hierarchy, it turns out that we could detect these meanings. And we're going to detect it by these magic test functions, which as soon as I get them straight in my head, 5 seconds later, they're not straight in my head. So, so I'll try and speak about them. This is the test function. It's going to test, it's going to take something of that type and see whether or not it's proper. This is going to try to. What's it going to do? Well, all it can do is the function is I'll apply it to some arguments. Okay, so those arguments are better do a good job. So what's a typical one of these arguments going to do? Well, it's going to believe that this guy's doing a good job. So it's going to look at these arguments and believe that this guy for its arguments. So there's a kind of recursion going on, but it's descending through the types. So if we're lucky, some inductive proof is going to work. And of course, we will be lucky. So one property that gets used, I think I won't go through the little proof. I'll just read it here. This lets us, it's going to let something work. I'll just see what it is. Suppose we've got T tau, we apply it to F S sigma, then you can pull this out and put it over here. That's the same as T sigma arrow tau applied to F. So we can, as it were, pull sigmas up until we've got rid of all applications to S's. That's going to be good because it's going to let some induction go through. I'm told you it was technical. Okay, so here's the central lemma. If we take any long beta eta normal form in lambda omega plus, then it's proper if and only if T tells you it's proper. So here's the proof. What we want to basically go by induction from here to there, but that has got some free variables in it. So we shouldn't go to there. We should go to that abstracted in all of those variables. So we're going to define Ni as Mi abstracted on the same variables that M is abstracted on. That's a smaller term, so we can do an inductive proof. Okay, so if we look at T of O of M, just by definition, it applies O of m to all the s's. So it's going to be s of sigma I naught, because that's the relevant one, the relevant argument, applied to these guys with the s's for the f's. But that's the same thing as the n, which is abstracted on the same arguments as m applied to the s's. So that's s some sigma sub I naught applied to on1 applied to the s's up to onk applied to the s's. Now what does s do? Well, it believes the t's are good guys. It's going to give you the answer. So s just takes the conjunct has least fixed point, the kind of it's corresponds logically to conjunction. It takes that, so it takes conjunction of these things. Now, using that, so we've now got something applied to a whole bunch of s's. We want to get rid of those s's. So we use that kind of commutation that we had in the previous slide, which I'll this one here. And we can pull them all out, and we eventually get to this place. T's applied, some t applied to the ONI, but these ONIs, these NIs are smaller than the m we started out with. So assuming that this was proper in the first place, by induction, these will all be top. So this whole thing will be top. So we've won, at least we've half won. The other half is what happens if it isn't proper. Well, if it isn't proper, one possibility is that this is omega. So anyway, the whole thing will have value omega. Otherwise, you do exactly this, you get to that point, and you'll by induction, one of these things isn't proper. So one of these things is going to be bottom. So it's out. So we've done a lot of work, but we've got a result. And now we can go down from lambda y to lambda omega plus. So let's see how that works. So suppose m twiddle. So we're going to go, what am I doing? No, that isn't the right thing to say. So, no, this is, sorry, that just remove that. Suppose that m represents, we have to show that m twiddle represents. So we have to show that, yeah, so actually, so what we want to show is that this thing is true. The m twiddle on some codes gives you a code if and only if m on some codes gives you the same code. That's what we want to do. That's right. That is not the right thing to say. So suppose m twiddle does, but then we have enough information about m twiddle. So m twiddle, so m8, so we want to show this with m instead of m twiddle. So we've got m-a-n, but m equals m twiddle with y substituted for the omegas. So we have the m twiddle without that. And as I said before, you can just substitute. There's a little bit of a technicality here, but I just want to skip over it. So you can substitute here. And so you can, so this whole thing, but this whole thing anyway is provably equal to m. So we're done. So that way is easy. The other way is also, well, slightly less easy. So now we want to get from m to m twiddle. So this is the central part of the talk. So we know we can do this with recursion. Can we do it with bounded recursion? That's what we're looking at here. So, well, we know that OM equals OM twiddle. Okay, so that tells you quite a lot. That tells you, we want to know whether M twiddle of that thing is proper. We'd like to know if it's proper. So we apply T to that. But since M twiddle and M have the same meanings, all of these things, oh, that's also a typo. This should be T of O of things. That should be T of O of things, yeah. So O of M twiddles equals O of M. So T of them are the same. So T of O of A is known. But I know this, but this is just a code in the type lambda-calculus. So it's certainly proper or equivalent to a proper thing because of normalization. So that's top. So this thing here is proper or is provably equivalent to a proper thing. So we're basically done, but not quite. So we know that this is a proper normal form B, but we actually need the B's the same as the A. How do we know that? We've gone down. Cutely at this point, we have to go back up just for a moment. If we know this, then by exactly the same argument as we had in the previous slide, we know this is the case with M instead of M twiddle. But we also know this, so A and B must be the same. So this was the right one after all. So we're done. So that's how we get down from a lambda y to lambda omega plus. I think I won't go through the technicalities of these things. It's just more technicalities, slightly different twists, but I hope I've got over the central idea, this fact that you want to do syntax, and wonderfully using domain theory, just a little tiny bit of domain theory, you can prove this, for me, unexpected result. So I've got some thank yous and a little 5-second speech. Well, one thank you is to Topos Institute. I'm hugely grateful, especially now that I've finished the seminar, for this opportunity to give the talk here and to be here and talk to you guys and everyone else. I want to thank Pavel Urchichin, who may or may not be listening. So this is work I did in 1982, it seems, when I was visiting MIT. And I totally submerged. I had no idea I'd done this until Pavel said, "Did you publish this?" And I said, "What?" And, and he sent me that. So these are notes. So this whole talk is some work. So I was supposed to give a little a contribution to Jonathan Selden's a volume, and I had no idea what to write. So I wasn't going to write anything. And then I thought, okay, I can write this. And also I thought it's going to make a really nice present for Dana, I hope. So thanks to Pavel for alerting me to that and sending me a copy of what I'd once written. And Pavel was also really useful and helpful in pointing out errors and comments on various write-ups. So thank you, Pavel. I obviously want to say happy birthday, Dana. It's great. I was here for your 85th. I was here for your, I don't know if I was here for your 80th, but anyway, now I'm here for your 90th. What could be more pleasant than being here and celebrating together? I can't think of anything more pleasant. I also want to say thank you, Dana. And this is not just for me, this is for a vast number of people. And celebrating here, I think, Dana's contributions to programming language theory. He has many contributions, but let's specialize in that. And I was thinking about these contributions. They're of different character. They're direct and indirect. And together, the field just wouldn't be without them. So directly, of course, we know there's domain theory. I can't imagine where we would have gotten domain theory without Dana, that bridge between logic and computer science. I don't know. Denotational semantics, again, it's a bridge from Tarski, who was Dana's advisor, with his denotational semantics of logic, pulling that over into type theory, lambda-calculus, and programming languages. It's so obvious, but the best ideas are so obvious. You try and think of a so obvious idea yourself, it won't necessarily come until afterwards. Then there's indirect things. So things came out of that. For example, LCF, Dana's logic, and the hands of Robin Milner became computer assistant theorem proving. And then other intellectual currents flowed in, the type theory of Martin Liff and Girard, and then we got the Koch theorem prover. That's one direction. Another way in which things can evolve is you take what someone's done, and then there's a problem. But that's absolutely great. There couldn't be a problem unless someone had done it in the first place. So here the problem was, okay, now we have semantics of programming languages. Every time the programming language has a computational effect, you have to write random stuff. Okay, but let's try and do that. Why can't we do it uniformly? So Eugenio brought in monads, and that solved that problem. And then monads got reflected into Haskell, and now we have a really interesting programming language there. So it's just like a river that starts with Dana's contribution and flows and expands, and more things come in and joins more rivers until we have a wonderful sea that we all live in, of programming languages and programming language mathematics and programming language use. So we all thank you, Dana. Thank you.
Don't forget all the beavers that live in it. 2 questions. Was your last result really showing that recursion doesn't help?
Yes.
Yes.
Doesn't help.
And so my other question is, instead of Sierpinski space, suppose you took D infinity as your.
Well, then you're back in the untyped lambda calculus.
Yes.
Yeah.
Where recursion does help.
Where recursion does help. Another place you can ask is a second order logic polymorphic lambda calculus. And there you have all, apart from many other things, you have all primitive recursive functions, including predecessors. So recursion immediately gives you everything. So it's a kind of a delicate place. Yeah, it's just that this little locality, it doesn't help. but
I'll get you to moderate questions because people won't be able to hear me at the back of the room. But first, I guess, any questions from this room? I'll solicit them too. Okay, then Andre Bauer has a question. Andre, Andre.
Hi. It seems like I can speak, but I cannot be seen. Hello, Dana. Happy birthday.
Dana the waves.
Can I ask my question?
Yes, go ahead.
Okay. So I was just a clarification. Gordon, is this a faithful description of what is going on? So first you argue that if you have something that's definable using y, then some finite unfolding where you stick in omegas when you prune will already do the work.
yes.
And then the second step you show that, and in the second step you also get rid of omegas, although that bit went a little over my head, so I don't understand how you did it, but then you also show that omegas are not necessary, right? Is that what you did?
Yeah, I mean, I was just trying to save time. I can go back and do the last step if you want to see a little bit of it.
No, it's okay. I've just tried to understand the overall argument.
Oh, yes. Yeah, it's in the slides, the last step. There's a little hint on it.
Okay.
There.
Okay.
But it's
Thank
not, the archive paper is wrong there. I need to correct the archive paper.
Okay, I promise not to read any papers of yours then for a while.
Yeah, it's in the slides, the last step. There's a little hint on
Okay.
it.
Okay.
But
Thank
it's
you.
not-
Okay, thank you.
Sure.
Sorry, that's a bit of a loop.
Okay, I promise not to read papers of yours then for a while.
Hank, I think you're unmuted. Would you like to ask a question?
Sure.
I want to say happy birthday to Dana.
Tina waves again. I think you're unmuted. Thanks. Would you like to ask a question?
I want to say happy birthday to Dana.
Some kind of loop. Yeah.
Yeah.
You might be watching a YouTube stream.
Oh, is that what's going on? It's just like, yeah, okay. Okay.
I have a question from Jan van Bush. Jan.
Yes, hello, can you hear me?
Yes, we can.
Okay, I can't seem to put my mic on, so my camera on, so I'll remain just with my picture. Okay, so yeah, my question is, since recursion doesn't help in this context, so the obvious question is, are there natural recursion operators beyond the typed Y combinator that would give us something extra, but not give us all the way all the partial recursive functions? So do we have any thoughts on that?
Oh, yeah. You mean implicit complexity or something?
Yes, or maybe I was thinking more of a polymorphic, more in a polymorphic type context.
Oh, if you go to the polymorphic lambda calculus, then all partial recursive functions become immediately definable.
Yes. So yes, I was thinking, is there a nice setting where there is an intermediate? I mean, where you don't immediately get everything, but you get more.
I think even like a Milnor polymorphism is probably too much. I'm guessing, because as soon as you have the for all x, x arrow x, arrow x, arrow x, I don't see one straight away. I just see some difficulties.
Okay. Thank you.
Question from Andres Gedro. Andre?
Hello, Dana, happy birthday. I wish I could be there on this wonderful occasion. Thank you very much, Gordon, for a wonderful talk. I was also going to ask about the polymorphic lambda calculus, but I see that this was just discussed. So let me then turn to the another interesting case. there are various versions of lambda calculus where only the polynomial time computable functions are defined.
Yeah.
So, Gordon, do you have any comments? What would happen to your type of arguments there?
No,
I mean, you want to have the recursion bounded there, but
you want even more than that, right? So
yes,
yes. The only thing I want to say there, and it's not even slightly answering your question, is that people, I should have mentioned, let's see if I can go back. So there's current work on automata theory and type lambda calculi by these folk here, and they work on various forms of linear logic. And they look at yeah, and they're looking at questions about definability in various forms of linear lambda calculi and implicit complexity, I think. So you could ask them, I guess.
Right.
But I think these are really
looking, as Dana said, you know, more things for Google Scholar. Looking forward to reading the papers.
More things.
Yes.
But yeah, and I think you'll see more. Yeah, there's a whole bunch of interesting. You're right. There are many interesting questions there. Yeah.
Right. Thank you.
Next, Luigi Licuri.
Okay, hello to everybody. Happy birthday, Professor Scott. Thank you, Professor Plotkin, for the nice talk. So I have a very simple question. So without recursion, my first thought that all programs are strongly normalizing because you use only simple types and determinates. So the question is, there is any relation with ad hoc polymorphism like intersection types? You mentioned Girard types, but probably intersection types, as Pavel shows in a seminal paper, are a little bit, does not characterize all the strongly normalizing program. Thank you very much.
So actually, maybe you can tell me. So if I take intersection types and I do Church numerals, what class of functions do I get?
Sorry, can you repeat? I didn't.
So I'm going to answer your question by asking you a question. If you take the type lambda calculus and add intersection types, do you know what numerical functions can be defined? Do you have any idea? Would you think that's different?
I think, I mean, I'm not a super expert of intersection types, but with intersection types, you get a complete characterization of all programs that strongly normalize. That is essentially the extra. Is like I mean, intersection types to my view are like a Swiss knife, theoretical knife to characterize termination.
Oh, I see. So that's as close as you can get to the untyped lambda calculus.
Yes, exactly.
So intuitively, adding recursion should just tip you over. Yeah, that's a great question. Thanks.
I should say thank to you, to Pavel, to Dana Scott, and not to this question.
No, it's great. All these different questions. Never thought of them at all.
So this probably should lead to a new race of proof assistant, where inductive construction could be simplified a lot.
I don't know.
For your next student.
I'm out of students. It has to be somebody else.
One question from YouTube is from a while ago, but I was sort of, why label the leaves? I'm not sure whether that question still makes. Why label the leaves?
Label the leaves doesn't make. Oh, he means in the trees, I guess. Yeah. Well, you have to have something there. Yeah, if they're finite trees. You could have no labels if you liked, and that would give you a slightly different data type.
Gordon, you said you're going to have a write-up of this for the Southern Spectrum.
I've already got a write-up, but it's got some errors in it. So that was very useful for this preparing this seminar, because you have to take things seriously.
I should clarify what I meant by noisy. It means not afraid to speak up. And that's a good characteristic property of our speaker today.
On that note, I don't think any further questions are coming in, so let's thank Gordon once again.
Great.
And let's say happy birthday today, no, it's not.
Happy birthday.